Hi everyone, my name is Michael and we are Team Groovy Network. Today our topic will be on network flow and transform and its applications. So what is network flow? Network flow is a directed graph where each edge has a capacity and a flow. To break that down a little, a directed graph is a graph made of vertices that are connected by edges with a specific direction, which can also be called arcs. Capacity is the number associated with each arc in the graph and denotes the maximum number that can pass. And lastly, flow, the number of items that pass through each arc. So the goal is to construct a flow, numerical values on each arc that represent the capacity constraints and that have incoming flow equal to outgoing flow at all vertices, except for certain designated vertices. So to show a real-world application of this problem, we have chosen to showcase a plane route. This is a top-down view of a plane route in the form of a flow network. Each node could represent a city. Specifically, node S is going to be the source, and node T is going to be the sink or destination. Each arc represents a flight route, and the number above it represents the capacity. You can kind of think of capacity as weight, because each flight route can only hold a certain amount of weight, and you never want to go above the max weight, or else that could lead to technical difficulties during the flight. And lastly, flow, which would be the amount that is held per flight route. So even though the capacity is 16 in this case, the flow doesn't have to be that number. It could be less than or equal to the capacity. An important thing to note is that the flow coming out of the source, S in this case, has to equal to the flow, the total flow I should say, going into the destination or the sink, which is T in this case. So there are many problems in network flow, but the 4 problems that we chose today are assignment, max flow, min cost flow, and generalized flow. Next, we'll be talking about assignment problem, which I'll hand off to Fiona.
Hi everyone, I'm going to talk about the topic of the assignment problem. The assignment problem is a fundamental combinatorial optimization problem. In its most general form, the problem is as follows. The problem instance has a number of agents and a number of tasks. Any agent can be assigned to perform any task, incurring some costs that may vary depending on the agent task assignment. It is required to perform as many tasks as possible by assigning at most one agent to each task and at most one task to each agent in such a way that the total cost of the assignment is minimized. So basically, you are trying to match different people with different jobs with the matching possible with the lowest possible cost. By using the Hungarian algorithm, we could minimize the cost. The intro of Hungarian algorithm. The first algorithm for the assignment problem is the Hungarian method, and it is also called the allocation algorithm. And the Hungarian method is a combinatorial optimization algorithm that solves the assignment problem in polynomial time. Here we will describe the first algorithm in detail and briefly show you how Hungarian algorithm work for solving the assignment problem with few steps. On the left side, this is the picture of 3 workers with 3 different jobs. Imagine we have 3 workers for 3 different location jobs, and we want to assign the workers to each job in a way that minimizes the overall travel cost. It is easier to convert the problem into an n by n matrix. So since we have 3 workers and 3 jobs, so we have a 3 by 3 matrix on the right side. And the number in the matrix represent the cost. Step 1. Find the minimum value in each row and do row reduction. This means each row now contains at least one zero after the row reduction. And step 2, column reduction. Next, we are going to repeat the step 1, but in column rather than the rows. First, find the minimum value of each column, then subtract each column minimum from every value in that column. This means each column now contains at least one zero. Step 3. Test for an optimal assignment. To do this, we draw a minimum number of straight lines on the matrix to cover all the zeros. If the number of lines is equal to the numbers of rows and columns, since we have covered the zero with 3 lines, which is equal to the number of rows and columns, and next, we can move to making the final assignment. Step 4. Making the final assignment. We chose the n0 where n is the number of the rows and column, and while ensuring that each row and column of the matrix only contain one chosen zero, and this zero in this matrix represents the final assignment of worker to jobs. To obtain the total minimum cost, we sum the value of original matrix that are in the same position as our chosen zero. So the total minimum cost for this matrix for this problem is 25 plus 30 plus 15, which is 70.
Next, I'll be talking about maximal flow. The maximal flow problem. Given input of a directed graph G and capacities on the arcs U that are non-negative integers, there's going to be two distinct vertices S, which is the source, and T, which is the sink, that are part of V vertices. The source is going to be the origin of the material of the flow, and the sink is going to be the destination. The objective is to find a flow F that maximizes the net flow coming out of the source, subject to the capacities on the arcs and the conservation of flow at the vertices. In short, the goal is to maximize the total amount of flow out of the source and into the sink vertices. Here's a quick example. On the left side here, we have a directed graph with capacities. From S to this node, the capacity is 5, and from S to this node, the capacity is 6. On the right side here, we have the same amount of graph, but now we have the flow that passes through each arc. In this case, from S to this node, the flow would be 5 over the capacity. And then from this case, from S to this node, the flow would be 2 over this capacity. It's important to note that the total amount of flow that exits the source has to equal the total amount entering the destination. So you can see here we have a total of 5 plus 2 flow coming out of the source, and 5 and 2 here, which equals 7, also coming into the destination. A good analogy for a flow network can be the following visualization. I kind of represent the edges as water pipes. The capacity of an edge would be the maximum amount of water that can flow through the pipe per second. And the flow of an edge could be the amount of water that currently flows through the pipe per second. That motivates the first flow condition. There cannot flow more water through a pipe than its capacity. The vertices act as junctions, where water comes out of some pipes, and then these vertices distribute the water in some way to other pipes. This also motivates the second flow condition. All the incoming water distributed to the other pipes in each junction. all the incoming water has to be distributed to the other pipes in each junction. It cannot magically appear or disappear. The source S is the origin of all water, and the water can only drink in the sink, which is T. Next, I'll be talking about algorithms for maximal flow problems. So the Ford-Fulkerson algorithm. It's a greedy algorithm that computes the maximum flow in a flow network. It's originally published by L.R. Ford Jr. and D.R. Fulkerson. The runtime of the algorithm is big O E times F. E is going to be the number of edges, and F is going to be the maximum flow in the graph. The three main steps of the algorithm is pretty simple. You first find an augmenting path, you then compute the bottleneck capacity, and lastly, you augment each edge and the total flow. To go over some definitions really quickly, the augmenting path is a path of edges in the residual graph with unused capacity greater than 0 from the source S to the sink T. In an augmenting path, the bottleneck is the smallest edge on the path. Let's go over a quick example. This is an example of a flow problem. We can denote this number as X and the bottom number as Y. X in this case indicates the amount of used capacity, and Y indicates the max capacity. Of course, S is the starting node, which is the source, and T is the destination or the sink. This is a possible path from S to T. As you can see, this is an augmenting path as all the edges have unused capacities that are greater than 0. We then compute the bottleneck capacity by computing the minimum from the path of edges, which in this case would be 8. We then augment the flow, which means updating the flow values of the edges along the augmenting path, which you can see with the red numbers here. The new values of X over the Y here, with X specifically indicating how much capacity is currently being used in the flow. We then try to find another augmenting path, which is in red here. We find the bottleneck capacity, which is 2 in this case, because from D to T, you can see that the previously used capacity was 8 out of 10. So to keep it from going over capacity, the max we can put is 2, or add to the values 2. We then update all the values along the augmenting path. In red, you can see is 2. Or 2, 2, and 10. We then find another path. This next path I have chosen specifically goes over the concept of backward edges. So even though the node is directed from A to D, it has a backward edge from D to A. This applies to all the edges. But the same concepts still apply. You find the bottleneck capacity that is greater than 0. In this case, it would be 4. You then update all the edges on the graph, including the backward edge. You can kind of think of this as redistributing the flow. Same concept applies. The first thing we do is find an augmenting path. You find the bottleneck or minimum, which is 2 in this case, as you can see here from S to A. You then update all the edges on the augmenting path. Again, we try to find an augmenting path, S to C, C to D, and so on and so forth. You find a bottleneck value on this path, which is in this case 3. And then you update all the edges on the path. And as you can see here, there are no more possible augmenting paths. Looking from S to A, the path is full. However, from S to C, you can see the capacity it's still 1. We can still push one more. But the forward edge, C to D, is full. And the backward edge, C to A, is empty. So we cannot augment the path anymore. Therefore, this problem is completed. Here's some pseudocode going over the algorithm. Same idea. Inputs given a network G equals VE with flow capacity C, a source node S, and a sink node T. And the output is computer flow F from S to T of maximum value. So another algorithm that works off of the fourth Fulkerson algorithm is called the Edmonds-Karp algorithm. First published by Yefim Dinitz in 1970. It was later independently published by Jack Edmonds and Richard Karp in 1972. So the runtime of this algorithm is big O and V times E squared. So vertices times edges squared. So this is essentially an implementation of the Ford-Fulkerson algorithm with one difference. So earlier, the example I showed you was specifically Ford-Fulkerson but also utilizing DFS, depth first search. But in general, while Ford-Fulkerson doesn't have a specific method to find its augmenting paths, this algorithm utilizes BFS. The path found must be the shortest path with available capacity. Here's the pseudocode for this algorithm.
So my topic will be minimum cost flow problem. So what is minimum cost flow problem? The minimum cost flow problem is an optimization and decision problem to get the minimum feasible way to deliver a specific measure of flow to a flow network. Some example in real life related to minimum cost flow problem is a supply chain logistics, warehouse transportation, passenger selection, and there are many others. So let's go to the definition. A flow network is a directed graph, G with vertex V and E. So with S, its source vertex we call it S, and a sink vertex T. They all belong to the vertex, where its edge UV belong to the setup edge E. Its edge has certain capacity CUV that must be greater than 0, flow FUV, and cost AUV. The cost of sending a flow along an edge UV is the multiplication between the F, which is the flow, and A, which is the cost. Hence, our goal is to minimize the total cost of the flow all over all edge, and the summation of those must be the minimum. Okay, moving on. So the algorithm that used to solve the minimum cost flow problem, one of that is called negative cycle canceling algorithm. So the negative cycle canceling is based on finding undirected path in the network flow. The residual capacity of the forward link is defined as Uij that minus Xij, and the residual capacity of reverse link defined as Xij. The cost of forward link is Cij, where the cost of the reverse link is minus Cij. So note that the forward link and reverse link definition is giving us the idea of what happens when we increase the flow or decrease the flow. So the algorithm basically has 5 steps. First step is to generate a random but valid flow, let's call it X. The second step is finding an undirected cycle which we can use Bellman force or the first sort algorithm that need to satisfy the cycle need to have positive residual capacity and negative cost. The loop will end and return X an optimal solution flow if no more cycle can be found. So the third step is to find the minimum residual capacity of the link in the cycle. Fourth step is adding that minimum residual capacity we found to all forward link in the cycle, but subtracting the same amount to our reverse link in the cycle. And the final step is return to test step 2 to find if there are any more undirected graph that not satisfied. So as you can see in the example below, we have vertex 1, 2, 3, and 4. So from vertex 1, there will be to vertex 2, there the cost of 1, 1, the cost is 1, and the capacity is transfer is also 1. From 1 to 3, there is 5, 3, the cost is 5, capacity 3. From 2, 3 is 1, 2, cost is 1, capacity 2. 3, 4 is 2, 3, the cost is 2, capacity 3, and 2, 4, the cost is 4 and capacity is 2. Note that if you can see the plus 2 and plus 2 on vertex 1 and vertex 2, that means it is the source node, and the minus 2 on 3 and the minus 2 on 4, that means they are sink node. So the node 1 can transfer azimuth 2, and the node 3 and the node 3 can consume minus 2. Also node 4 can consume minus 2. So moving on, following the algorithm, we use Bellman force or the first search to find that the undirected circle in this particular example is 2, 3, 4. So now we just assign a random x. So the flow from 1 to 3 is 2, flow from 1 to 2 is 0, 2 to 3 is 0, 3 to 4 is 0, and 2 to 4 is 2. So next, we will find the minimum residual capacity of the link in the cycle. So note that the residual capacity from 2 to 3 is 2, 3 to 4 is 3, and 2 to 4 is also 2. So the minimum capacity will be 2. So by adding the minimum residual capacity on all the forward links, so right here if we see 2 to 3 on forward link, so we'll add 2 to that. So 2 to 3 flow will become 2. 3 to 4 also forward link, it will also become 2. But then the from 4 to 2 is a reverse link, so it will be minus 2, so that node will become 0. So as you can see in the picture, it becomes 2, 2, and 0. So to continue, we also see from vertex 1 to 2, 1 to 3, 3 to 4, and 2 to 4, also an undirected cycle. And so now we need to find the minimum residual capacity here. So we can clearly see that the minimum residual is from vertex 1 to vertex 2 with capacity is 1. Then we follow by the same step that we have. The undirected cycle that we found here is 1, 2, 4, 3, and then go back to 1. So the minimum residual capacity is 1. So 1 to 2 now will become 1. 2 to 4 will also become 1. 4 to 3 is 2 minus 1 also become 1. and 3 to 1 is also 2 minus 1 becoming to 1. So here is the final solution that you see it had the minimal cost is possible. So the total cost of the graph will be cost of 5, which is from 1 to 3, cost of 1 from 1 to 2, which is 6, from 2 to 3, the cost of 2, which is 8, from 3 to 4, cost of 2 also, so which is 10, and from 2 to 4, cost of 4, so 14 is the final minimum cost. So next, we will go to the minimum cost flow application in real life. So to be summarized, we can summarize as follow. We got two factories that introduce some number of units. Each, we have demand to separate warehouse that require a certain number of units for each. And then it turned out we have sort of a middle point, call it distribution center, that you can ship product to from the factory and then ship it out to the respective warehouse. However, there are also directed way to ship from factory to the warehouse, and that is by the railroad. And so we have unlimited capacity on the rail link, but if we ship to and from the distribution center, we have a maximum capacity that we can ship is 50 units for its leg of that journey. So the optimization probably is really to identify how many units, which is in this case, by the way, the truckload should be shipped along its shipping lane, and how many should go to direct from the factory to the warehouse by rail, and how many should take the way to the distribution center. So moving on to the graph presentation. Again, here we see that we got factory 1 and factory 2 on the left with the associated amount of available unit that can emerge from each of the factory. And on the right, we have the warehouse that are demanding a certain number of units. And as you can see, the very top link is we have the ability to ship directly from factory 1 to warehouse 1 by rail. We also have the ability of the very bottom to ship directly from factory 2 to warehouse 2, again by rail. Now we mentioned that a distribution center sort up in the middle of all of this, and we have the option to send truckloads from factory 1 to distribution center, or from factory 2 to the distribution center, and then we can ship from the distribution center to either warehouse 1 or warehouse 2. There right now, note that the products are the same, meaning the products are interchangeable. The one that are created on factory 1 versus the one created on factory 2. So we are really only dealing with one source of one type unit. So now to be more concise, we go to the next slide. We have the description of the network model, but we have added some data. We still have the amount that produced from the factories and the amount demanded by the warehouse. But now on each of the arcs, and an arc is represented a connection between any two locations in the network. So for example, the top arc connects from factory 1 to warehouse 1. And so this very top lane again it's got an arrow with head on it, and it implying a particular direction that the unit can flow. And we also got a cost now associated with that arc of possible flow. What that means is for every unit that we send from factory 1 to warehouse 1 will incur along this direct rail. At the very top, will incur a cost of $700 for each unit. So each arc now is characterized by cost to move one unit along in the direction of the arrow. So you see that if we use we go to the direct distribution center, we'll have to incur a separate jog length moment. So if we go from factory 1 to distribution center, we'll incur a $300 per unit transportation charge. If we move from the factory to the distribution center, we incur a 500 unit charge again. So particular cost for unit for the outbound lane out of the distribution center now the one or the set of data in addition to the cost and that the capacity. So we have a maximum of 50 truckloads that can be sent along any of the lane. So that given in the square, which is 50 unit max, we can zip along the lane from factory 1 to the distribution center. And from the distribution center to corresponding outbound lane to either warehouse 1 or 2, also carrying a max of 50 units now. So next we'll go to a more closer look to the network model. So you see we have identified all the nodes F1, W1 to W2 and distribution center. But now you see the in the square parenthesis next to it node is a representation of the amount of capacity available in the case of the factory. But you notice the negative number corresponding over here to it of the warehouse node is negative 60 on W1 and negative 90 on W2. So basically, as I talked before, those numbers are the demand nodes. And so you see in the case of positive value for the network, it is the amount of units that must be sort of pulled out from the network. And in other words, we view the factory 1 and the factory 2 as supply node. They are supplying unit into the network, and W1 and W2 is being demand node where they need to consume or absorb the units from the network at a final destination. So as to the square around the in the parentheses around the distribution center have a value of 0. This typically is what we call a transshipment node, and that the product is neither created at the distribution center or consumed at the distribution center. It's just really sorted by path to location. And again, that a typical function of a distribution center is to bring the shipment in and maybe consolidate, mixing them up and change them and whatever, and they can send them out to the other end. They don't actually create or consume unit. In that way, we still have our capacity associated with the truck, the truck arc and the truckload arc, and we also have all of our unit transport cost labeled on this model. So this has all the data that we need now to formulate and solve this model. Some terminology of the model of any minimum cost flow problem is represented by a network with a flow passing through it. The circle in the network are called nodes. So you can see the F1 and F2. So it knows where the net amount of flow generated is a fixed positive number is a supply node. So you can see the 80 and 70 is a positive number, and so we call it a supply node. So it knows where the net amount of flow generated is a fixed negative number in a demand node. So you can see that on W1 and W2 also. It's called demand node. And any node where the net amount of flow generated is a fixed at 0 is a transshipment node, having the amount of flow out of the node equal to the amount of flow into the node is referred to a conservation of flow. The arrow in the network are called arcs. The maximum amount of flow allowed to an arc is referred to as the capacity of that arc. So our assumption for solving the minimum cost flow problem is we have to assume that at least one of the nodes is a supply node, and at least one of the other nodes is a demand node. All of the remaining nodes that not a supply or demand, then it should be the transshipment node. So flow to an arc is only allowed in the direction indicated by the arrowhead, where the maximum amount of flow is given by the capacity of that arc. The network had enough arcs with sufficient capacity to enable all of the flow generated at the supply node to reach all the demand node. The cost of the flow to each arc is proportional to the amount of that flow, where the cost per unit flow is known. And the objective here is really to minimize the total cost of sending the available supply to the network to satisfy the given demand. One last point, but also the most important one, is under the previous assumption that I've said, the minimum cost flow problem will have feasible solution if and only if the sum of the supplies from a supply node equal to the sum of the demands as its demand node. So finally, the solution of this problem is
The intro of the generalized flow problem. The first simple combinatorial algorithm were developed by Drew and Onaga. Kapor and Vaidya developed technique to use the structure of the matrix that arise in linear programming formulations of network flow problem to speed up the interior point algorithms. The characteristic is it is very similar to minimum cost circulation, and also is a special case of linear programming, can be solved in polynomial time using any general purpose linear programming algorithm. The current Fatis algorithm for the generalized flow problem due to Vaidya is based on a interior point method for linear programming and runs in the big O of m to the power of 2 times m to the power of 1.5 times log of b time. So this is the running time, the fastest running time for this algorithm. And it combines the idea from the paper of Kapor and Vaidya with the current fastest linear programming algorithm, which use fast matrix multiplication. And the basic definition of generalized flow problem. The generalized flow problem, also known as the problem of flows with loss and gains. For example, oil or gas shift through the liquid pipeline. A loss happens in the way. Second, imperfection in a raw material entering a production process. Third, spoilage of food item during transit. The same amount of food you send out from the supply node, and when you reach the demand node, you may not receive the same amount because of the spoilage. A loss happened. fourth, fifth during transit, fifth, interest or dividends on the investment. This problem requires some modeling change. Here we have an example of generalized network flow problem. We have 4 kinds of paper with different costs and yield for process 1 and 2. As you can see, the table on the left corner, downside here. For each supply size, we have corresponding cost and yield. For example, if you have 1 ton of newspaper, for the process 1 will give you 0.9 tons of pulp, whereas process 2 will give you 0.85 tons. Process 2 price is cheaper but gives you less pulp for recycling. And you could easily tell the supply is greater than the demand by the above information. The total supplies is 70 plus 50 plus 30 plus 40 equal to 190 tons. And the total demand is 60 plus 40 plus 50 equal to 150 tons. So, are we able to tell the supply must be greater than the demand? But the question is, you don't know how much is the loss during the process. So supply could be greater than the demand, less than the demand, or equal to the demand. So how we handle this problem is we assume the supply is greater than the demand. And this is the network for network flow recycling problem. Here we have a supply zoom on the left side with the cost and yield. In the middle is transshipment node, which are 2 recycling process, and here are some costs associated with the recycling transshipment node. In this network, our goal is to minimize the total cost in entire recycling process, and we want to determine how much tons of supply node sent to the demand node. For the objective function, for each arc in a network flow model, we define a decision variable as xij. It represents tons moved or sent from the node I to node j. We don't use word transport to describe the process because some loss happened during the process. Here we have the minimized cost formulation. We plug into cost with each arrow to get the minimized cost for the problem. Arrow x15 times the cost, which is 13. So the total minimized cost is the sum product of all variable and cost associated in the network and being provided in the table. And here we will briefly outline 2 important algorithms for the generalized network flow problem. The polynomial time combinatorial algorithm. The Goldberg-Plotkin-Pardus algorithm, which we shall call algorithm NCF, considers all arcs. The main idea of the first polynomial time algorithm of Goldberg-Plotkin-Pardus is best described by contrasting the algorithm with true-ampers. In each iteration, both algorithms solve a simple flow problem and interpret the result as an augmentation in the generalized flow network. The true-amper algorithm augments the flow along all the cheapest augmenting paths at once using a maximum flow subroutine. And you can take a look on the inner loop of the true-ampers algorithm. By the discussion above, The algorithm finds maximum flow from the node which exists along the highest gain path to the sink. But the true Ampere's algorithm also has a downside. The downside is the true Ampere algorithm is slow because at each iteration it considers only arcs with units, will label game, and some of the arcs adjacent to the source, disregarding the rest of the graph completely.
For our last section today, we will be talking about network transform. As a recap, we can make 3 assumptions about network flow problems. First, all the arcs are directed. Second, all costs are non-negative. And lastly, all lower bounds on arcs are 0 and all upper bounds are positive. If the above conditions are not satisfied, we can then transform the network into one that does. Here are the brief steps to do so. You want to first convert undirected arcs to directed arcs. You next want to remove non-zero lower bounds, eliminate negative costs. After that, you want to remove arc capacities that lead into node splitting, and then reduce costs next, and to finish off is residual networks. The first step, convert undirected arcs to directed arcs. You want to replace each undirected arc, ij, by 2 directed arcs, ij and ji. Assume that the cost of this arc is greater than or equal to 0 and lowers of 0. You want to remove non-zero lower bounds. After that, you want to eliminate the negative costs. To do that, you reverse the direction of any arc ij with negative costs. The new arc ji cost is negative c ij. After that, you want to remove arc capacities. Here's a small illustration demonstrating the transformation for that. The next step would be node splitting. So node splitting involves taking each node, which you can denote as I, which has arcs going into it and out of it, and replacing it with 2 nodes, or you can name as I1 and I2, or in this case. So the first one would handles all of the outflow from node I, and the second one accepts all the inflow. A single arc, as you can see here, connects the split nodes. By placing a capacity constraint on the arc over here, we effectively limit flow through the node. Reduce costs. Because some network flow algorithms work by assigning potentials to each of the nodes, we can define a new network flow problem that uses reduced costs instead of original costs. The reduced cost transformation should not affect the total cost of the cycles. The total reduced cost should always equal the original cost, as you can see denoted by this equation down here. And lastly, residual networks. We can define a residual network with respect to a feasible flow. As you can see here, we are constructing the residual network. And that's it. Here are the references, some of the references I should say, that we use for our presentation. And thank you for listening today.